All right, we're going to talk about lesson 7.5, which talks about three basic things. It talks about the triangle proportionality theorem, the converse of the triangle proportionality theorem, and the mid-segment theorem. I'm going to group the first two together, and I'm going to do a video on the first two, and then I'll do the second one separately. So there is a theorem that says if you have a triangle and these two sides are parallel, remember those little arrows tell you that those sides are parallel, that these parallel lines will break the sides up into proportional sides. Now, please remember, it has to be the sides. It can't be like this base that is. It has to be the sides that you set up. So if I draw out this particular triangle that they have here, again, a little bigger so we can see it. This is P, Q, R, S, T, and it says these two are parallel, so those two are your parallel sides. And it says that this side is 32, this side is 16, this is X, and this is 12. So it'll tell you that this side is proportional to this side as this side is proportional to this side. So I can write a ratio. 32 over 16 has to be the same ratio as X over 12. Well, now this will allow you to actually, whoops, you can't see that. There we go, sorry. This will allow you to now solve this ratio. You can cross multiply 16X equals 32 times 12. So you're just going to take your calculator and say 32 times 12 will be 384. And now in order to solve for X, you're going to divide both sides by 16. So you're going to take 384 divided by 16, and you're going to get X equals 24. So that's one way. So that is how you can use this proportionality theorem in order to solve a variable, so to find X. Another way you can do it, though, is called the converse of this, which is kind of like using it backwards, if you will. So now that we know that that side was 24, let's write that in, 24. And let's get rid of these parallel symbols. So now you can use it backwards. They have not told you that those sides are parallel. Remember, if there's no marking there, you cannot assume that they are parallel. Even if they might look parallel, of course, the way I drew them, they don't, but even if they look parallel, you cannot assume they're parallel until the markings tell you that. But if you can prove that this to this is the same ratio as this to this, then you can prove that those two sides are parallel. So if you said 32 over 16 is the same as 24 over 12, if that relationship is true, then those lines must be parallel. So again, 32 over 16, I can divide both by 16. That would be 2 to 1. 24 over 12, I can divide them both by 12. This would be 2 to 1. Since these ratio 2 to 1 to 2 to 1 is the same, then therefore I can prove that those two are parallel. So that's how you use this particular theorem in a way to solve for X, or a way to prove two sides are parallel.